So I'm Vicky. Yeah, I came from Shopify and I worked on the data ingestion team at Shopify and did a lot of work with Apache Iceberg. So what I'm going to share is kind of the evolution of what I have experienced in industry and also highlight some of the unique features that Iceberg offers to allow us to do ingestion at scale. So when we talk about data ingestion, one of the biggest portions of the data ingestion story is how we get raw data from external sources into our data lake. So raw data can be in the form of, I want to mirror this database table. I want to get this third-party data into my system, like maybe you integrate with Salesforce or Zendesk, I need to bring that in, but it can also be event-driven. It could be click streams, it could be IoT logs, all of that. And when we talk about techniques for ingestion, basically techniques fall into one of two camps. Basically, there's batch ingestion techniques and streaming ingestion techniques, and they both have their pros and cons and different technologies to enable that. So I want to start off by first tackling the batch ingestion story. I'm going to walk you through what this looks like specifically for the use case of database table replication. So when we do database replication, one of kind of the first naive ways of going about this is using statement-based replication, which is when you just run a query against a database to get a bunch of data out. So this happens very naturally. You're a startup, you don't have that much data. Someone is like, I need this table somewhere else, maybe in BigQuery, whatever the system is that you're using. I need it out so I can do some analysis on it. So maybe you start with a simple scheduled query like select star from table. Really easy, it works, but it doesn't scale, right? Your tables get larger, you grow as a business, this stops scaling super, super quickly. So you say, well, I don't need to pull the entirety of this table every single time. Let's just pull the updates. How can I just get what's changed out of the database? So maybe you introduce, or maybe your tables already have some sort of incremental key. So here I've added this where clause where updated at is greater than a timestamp, some sort of timestamp that's when I last ingested from this table. So this works great, except that we have to trust that this field on my table, this updated at key, this incremental key, is indeed getting updated when updates are happening to the row. So maybe you have a database that's triggering triggering that field to get populated, or maybe you're relying on application developers to actually properly modify that column. And if it's not getting updated properly, you have this possibility of missing updates. Finally, as your business scales, this will also stop working and we'll have to come up with something else. So let's create smaller queries. Let's do some sort of bucketing approach. Let's limit the number of rows I'm asking of the database every single time. So here, what I'm doing is I'm limiting myself to only gathering 10,000 rows of data at a time. So I can run this query in sequence. But again, it's in sequence, it's not parallelizable. I will at some point run into scaling problems. What if I pre-compute all of my queries? So I can create these like time ranges. I can pre-compute all these queries and then give them off to a bunch of machines or threads, and they can run great. But now my application developers, my database developers have come to me and they say, hey, you are running tens and thousands of queries against my database. This is the production database. We don't like it. This is like creating contention on the database, which is supposed to be for operations. Do something else. So basically what we've done is we've exhausted this technique for ingestion. We have to move on to something else. One other thing I would like to note here is whenever we do statement-based replication, we have no way of capturing deletes. There's no way for me to ask the database what is no longer there. So just to keep that in mind when you use this sort of replication technique. So can we do better than all of this that I just mentioned? So let's dive into some streaming options, streaming ingestion. So streaming in general, eventing in general, there's a lot of different forms, a lot of different data that you might want to stream in. So there's click stream data, there's change data capture data. So that's when we see events for every single row level update to a database. You might have domain events, so that's a special kind of analytical event. But regardless of what your stream of data looks like and what it represents, there's some common challenges. Those challenges include the transactional semantics of ingestion, like how do I actually get transactional guarantees from my streaming distributed system to my analytical distributed system. And also there's some query performance challenges when it does come to stream ingested data, because we are committing data to our data lake or our Iceberg tables quite frequently. So I want to keep talking about this theme about mirroring this database table. So we're going to use a different technique now. We're not going to use statement-based replication. We're going to use CDC, change data capture. And for those that don't know, the way that you do CDC on a relational database is you tail what's called a binary log. And this binary log of your database is essentially a transactional audit log of every action that's happening to the database. So we'll have events for every create, update, delete. You will even have events for every read and actually query that's performed on the database. And this log is typically used for database replication. So there's a bunch of tools like that people use to be able to do this, but I want to spend time on the second portion of this equation, which is actually going from the Kafka topic or your streaming infrastructure to your Iceberg table. And you can use a variety of tools to do this, like Kafka Connect, Flink, Spark. But what I would like us to spend this time on is less about the technology of what you can use to do that and more about what's so special about Apache Iceberg that makes it a good choice for streaming. So it doesn't matter what technology you use. The great thing about streaming is that usually your stream is partitioned. That means I can have independent consumers from each of those partitions. Each of those consumers ends up being a writer to my Iceberg table or to like my data lake. And the core piece of Apache Iceberg is the catalog. And very quickly, you'll look at this diagram and say, hey, I'm going to have a bunch of different writers all wanting to commit to my catalog at the same time. This seems problematic. So what we're going to go over is how Iceberg does commit coordination and specifically dive into the atomic transactions that Iceberg supports and optimistic locking. So before I go into how Iceberg does atomic transactions, I want to go back in history a little bit and look at HDFS, Hive metastores, object stores, and how transactions are done in those systems. So back in the HDFS days, Hadoop distributed file system, it was really common for people to use this pattern of creating some sort of staging directory, having their process run. So this is, you have same pattern in the batch or streaming world. You would have some sort of staging directory, write all your data there, and only once your process has verified that all the data is correct, you have everything you need, you're ready to publish it, you would perform a rename to make it available to consumers, to your data scientists. So this rename was actually an atomic transaction. So once you perform that rename, all the files in that directory that you're renaming would become available. This is not the case in object stores. So with the advent of cloud computing and cloud vendors, S3, GCS came to be, and people moved away from HDFS and adopted object stores. And on the surface, it looks really similar to HDFS, but under the hood, it's quite different. It does not have this file system like abstraction. And what that means from a functional point of view is when it comes to these renames, so a directory or file rename, they're not atomic. So if I want to rename a directory, it's actually performing a copy under the hood. So if I use that pattern that I was using the HDFS days of renaming everything here, each of those files would perform a copy into the new destination directory. And if someone's reading that directory, a consumer, it's possible for them to see partial data. So then came Hive and Hive Metastore. And with Hive, you could have transactions about making folders and directories visible. But the one caveat here is late arriving data. In the streaming world, late arriving data is the bane of any data scientist existence. And if I have all these partitions that are already made available in my Hive Metastore that have already been published, if I need to add or modify data in one of those locations, it's not done atomically. So for example, I have a process that maybe fails. It's writing those files and then fails. There's no way for me to go clean up, or it's quite difficult. I have to create my own system. I don't get this out of the box. And when that process starts back up and tries to write again to these directories, I could end up with duplicate data, all this junk data. So all of these systems, basically, I don't have atomic acid transactions for covering the whole data as a whole. And this is problematic. So what does Iceberg do differently? So I really like to compare Apache Iceberg to a file system, like a traditional file system on top of a hard drive. If you think of a file system, it's really an abstraction where you're keeping track of the position, what's the address of these files on the hard drive, right? It's just a bunch of pointers. And Iceberg is doing something very, very similar with all of its metadata files. Its metadata files are referencing where those data files actually live as part of the table. So if I add other data around it in the same directory, maybe, that data will not be visible until it's incorporated in the metadata and then finally published and committed to the Iceberg table via the catalog. So the catalog ends up being this very, very important piece that gives us atomic transactions. And I think this will become very clear when we walk through an example and demonstrate optimistic locking. So we're back to our streaming use case, and I have a bunch of writers, multiple writers, and say I am writer number one. I'm writer number one. I have a bunch of changes. I want to commit it to the table. What do we do? So the way optimistic locking works is first I talk to the table and I get what the current table state is. Great. So I know what the table looks like. Now let's write all the metadata to express what the table looks like with my changes. I write all of that down to disk. And when I say write all of that down, my data files are already there. I'm only creating the metadata files required to express my change. Now everything's written to disk and I'm ready to make it available. So to do that, I grab the lock of the table and I check to see if the state of the table is the same as what I think it should be. So basically I'm checking, am I placing my changes on top of the table? Am I going to be the latest set of changes? And if yes, then I'm going to swap out the ledger, this like metadata file in the catalog. If no, I'm going to repeat this process again. I'm going to get the new state of the table. I'm going to write new metadata files, grab the lock, do all that and repeat. And now you might be thinking, well, if I'm not on top, I might go through this loop several times, especially in the streaming use case where I could have several tens of writers that are now competing for the catalog to publish changes. And the thing is, you're correct, that is true, except that the only thing that I'm having to rewrite are these top level metadata files, which are quite small. We're talking megabytes in size, not gigabytes in size. There's no movement of data files, these Parquet files. So this actually is quite cost effective. So are we good now? Almost. We still have some problems. We still have some problems. We're able to commit all these changes to the Iceberg table, but we still have some problems with how that data got there in the first place. And specifically, how frequent are we committing to the table? So when we talk about streaming, one of the things that you think about is, what do I want my lag to be between my source, so my stream, and my destination, my data lake, my Iceberg table? So that could be an hour, 30 minutes. Maybe you want it to be quite small. Maybe you want your lag to be only 1 minute. So you're consuming data and you're consuming it for 1 minute, and then writing the files, committing it to the Iceberg table. Are you going to get the optimized file size for the data you ingested in just 1 minute? Probably not. These files can be quite small. So we're going to have this small file problem of writing tons and tons of small files, and small files are going to create query performance issues on the read side. The other thing is, if I'm committing super frequently, there's going to be so many changes that my Iceberg table is going to keep track of. This is going to get very expensive very fast. So one of the features of Iceberg is its maintenance tooling. So it has a bunch of different maintenance features and tools to take care of the small file problem and all this history. So we have file compaction that will take a bunch of these small data files and compact them into larger ones that are more optimized. So typically you aim for 512 megabytes. It might be different in certain situations, but we're taking these small files, putting them together. Similarly, with rewriting manifests, we're doing the same thing, taking a bunch of these metadata files, rewriting them into larger ones. And then snapshot expiry. Snapshot expiry is when we're saying we only want to keep track of maybe the last 24 hours, maybe 1 week of changes to the table. I don't want to do time travel to every single point that I have ever committed to this Iceberg table. That can end up being a lot. So you'll configure it to be like, I only want to keep the last 24 hours worth of changes, commit changes to the table. So that's all well and good, but none of those 3 actions I mentioned actually removes data from your object store. Those will create new files, change pointers around. So we need something to actually clean up all the junk that is left over on your object store. So this is where orphan file cleanup comes in. An orphan file cleanup will look at what's registered in your Iceberg table and remove any files that are inaccessible. So anything you can't access, the Iceberg table no longer references, those are all candidates to be removed and cleaned up. So everything I talked about sort of makes sense in the realm of appending data to your table. But going back to the beginning of the presentation, we wanted to create this mirror of my production DB in Apache Iceberg. So this actually requires an upsert, a modification of data. I want to take a row and I want to modify it. It has new values now. Iceberg offers 2 different ways of expressing an upsert. So you can do what's called copy on write or merge on read. So copy on write is what you expect it to be. This is a traditional case of like, here's a whole new set of data files that represent exactly what I want. It's a complete replacement. Merge on reads a bit differently, works a bit differently, where we express data to be filtered out to actually perform an upsert. So it does this in the form of introducing the concept of delete files. So in the V2 spec of Iceberg, it adds delete files. It comes in 2 flavors, positional and equality deletes. I'll get into those in a second of how they actually work. But the value of presenting these deletes or like these filters is that I actually get to procrastinate rewriting the files on disk. So I can almost work in this append-only fashion of appending data files, appending these delete files, and at query time by your engine, so Trino or Spark, it will actually do all the filtering for you to get the same result. So you might think that this is actually a lot of work that has to be done by the engine at read time, and that's true. But we'll go into a little bit of like why or why not you'd want to use this technique. Finally, you have targeted rewrites. So we're talking about compacting those data files. So we can still compact these files away because it'll always be more efficient to not have to do this on the read side. We can schedule that to happen with Iceberg. But let's go into like why I wouldn't always want to rewrite these files all the time. And the reason being is that it's actually quite time consuming and expensive to perform an upsert. And the reason for that has to do with the fact that we're storing all the data under the hood using a columnar file format. So that could be Parquet, it could be ORC, but these columnar files, the way that they're formatted is you co-locate all the column level data together for all the rows. So I have a bunch of data, I have a bunch of rows. I'm going to have all the data for column A together, and then all the data for column B together, and so forth. If I want to do a modification, say I want to delete or add a row to this file, I'm going to have to make a modification in multiple places in the file. So basically, I have to open up the whole file. And because of that, we call these files essentially immutable because I have to reopen the whole thing, make the change, and write it back down. This is an expensive operation. So finally, I'll go into a little bit to demonstrate exactly how merge on read works. I mentioned that there are two flavors. There's equality deletes and positional deletes. So the way equality deletes work is I have my base table. This is like my Parquet file, my Parquet data file, and I append to my table I'm calling it a delete file that represents a column and a value. So in this case, I'm saying for a column ID, where the value is 25 or the column value is 45, filter that row out. So what will happen on the query side of like Trino and Spark, it will filter out that row with ID 25, and I'll be left with this result. Similarly, but differently in the positional delete case, this is represented slightly differently, where instead of saying like these values have to match, I'm specifying exactly the row I want to be filtered out. So I have the file. So here I say file number 1, Parquet. I would like to filter out a row from that file, and that row is position 2, so the second row of that file. So that corresponds to that row here, and that one gets filtered out at the end. So what's unique about this is actually if I have multiple changes for an ID, the same value. So you see like ID 45 here and ID 45 again. So I have a create operation and a delete operation. I can be very, very specific of where I want that delete to happen. So I'm going to keep that final row to have that at the end. Cool. So I hope that was insightful. So just to like recap what we talked about some of the limitations and struggles with batch ingestion when we are trying to mirror a table from a database to Apache Iceberg or just like any system in general. We talked about streaming and CDC and some of the core features of Apache Iceberg to actually make streaming accessible, and that's with its atomic commits and optimistic locking. And then we did a little bit of a deep dive into the merge on read and copy on write functionality of the V2 spec and how that can enable, give you some nice levers and choices around how you want to communicate upserts in your system. Cool. And now Jason is going to do a bit of a demo of some of these features in Tabular.
Awesome. Thank you, Vicky. Actually, will you bring those slides back up again? I'll just talk through a few slides and then I'll get to the proper demo. I also want to mention that there is a Q&A on for the webinar. So if you've got any questions about anything that Vicky has talked about or just broad questions about Iceberg or anything I'm about to talk about, then please do drop them in the Q&A and we will definitely have time at the end to address some of that stuff. So Vicky talked through sort of very generically, batch and stream ingestion, also how Iceberg really helps those things. If there's any question that you can do all this at an intense scale with Iceberg, at Netflix, and I'm probably the same at Shopify Vicky. We were using these patterns to both batch and stream ingest hundreds of petabytes, I feel like, a day, yeah, or at least tens of petabytes a day into the Netflix warehouse. So these things scale incredibly well. It takes a lot of pressure off that, off say like the Hive Metastore. Hive Metastore was a clear bottleneck in a pre-Iceberg world, and now because all these operations are happening with the file system and they're all distributed, it scales much better, and you can get great performance. And we can get data right into our Iceberg tables and make it available for analytics. Really like lower the latencies, particularly with the stream patterns, than we could in the older systems. So I want to show some examples, and go ahead to the next slide, Vicky, and talk about two big features within Tabular that address sort of these batch and stream ingestion use cases. So the first one is a file loader. This is our automated batch ingestion feature. And what this is really is a serverless system that allows you to, just through configuring a few Iceberg table properties, will automatically load data that lands in S3 in a variety of formats, and load that up into your Iceberg table so that it can be used for any downstream consumption for analytics or for further ETL. And so here's a couple of the properties, and there's more things you can configure here. But basically, you can apply, hey, what is the file format that you are going to be ingesting? It could be JSON or Parquet or CSV and others. How do you want this data to be loaded into your table? Do you want it to be appended, or do you want it to be a full replace? And those are the only modes for this particular batch ingestion. We can't do more complicated things like upsert. We'll talk about that more later. But in this, we can either choose to, hey, replace the entire table. So that's like in Vicky's example, we're talking about, we're just starting out. You just want to say, I want to dump my entire table to S3 and then have it available in my lake. You can use a replace. And as you get more sophisticated and maybe you're doing smaller incremental batches from your transactional system, you can just append those into your Iceberg tables. And you just provide a path on your storage, and also handles like some of the trickier pieces. We didn't talk a lot about this, but one of the key things when you're dealing with batch or stream ingestion is how do you deal with schema evolution, right? The reality is like your source databases or streams or events, those schemas evolve over time, and it's difficult sometimes to coordinate those changes from the application world into the analytic world, into the data warehouse world. And so, automatically handling schema evolution is a big challenge, and something that the tabular system does quite well. So that is that. I'll show these in the demo as well. Just go to the next slide. Is just the architecture of how this file ingester works. You're going to have, your S3 buckets and a landing zone for the raw files, whether that's, again, dumps from your database or your landing stuffs from, a Kafka Kinesis stream. You land that data into somewhere in a storage bucket, and then you configure S3 notifications to be sent from those buckets to Tabular, right? So any new object that lands, Tabular is going to get notified that it's there. We're going to batch those up and try and get a bunch of small files potentially into a single batch. We're going to go read those off of your S3 bucket, and then apply the table schemas, do all the schema evolution work, and then write them back out as optimized Parquet files. So even if you started with like JSON or CSV, you get a nice optimized schema Parquet files with a managed Iceberg table out the other side. And we'll see that in action here in a second. And then the other thing that I'm going to show in the demo is on the next slide is the Kafka Connect. This is something that Tabular has open sourced, and it's handles a lot of the challenges that Vicky alluded to from the stream ingestion world. So you don't have to run a whole lot of infrastructure. You can just, through configuration, say, hey, I want to read data from these set of Kafka topics. I want to write them directly into my Iceberg table. I'm going to use Tabular as the catalog. Tabular provides this REST catalog interface. And you can do a lot of configuration options, but there's some very simple things to make it easy. So it will automatically create new tables as it sees new events for new tables coming through the stream. So you've got this all set up, say, to read from that from that bin log from your transactional system, even as new tables get created, those can automatically get created in your warehouse without having to do any additional work. So that's pretty powerful stuff. Again, schema evolution, being able to take a single topic, Kafka topic, and fan it out and route it to multiple different tables. That's also a very powerful pattern because you may have a single topic that has all your changes from your transactional system. That may be hundreds of tables, and you want to fan that out to hundreds of Iceberg tables on the other side. So you can get this mirrored effect. And then controlling how frequently these commits happen. And again, there's trade-offs here, and we'll talk about those, right? The smaller window those commits happen in, the more small files you're going to create. But luckily, the Tabular platform automatically handles a lot of those maintenance activities that Vicky alluded to. So we'll see that in action here in the demo. You don't really have to worry too much about compacting small files or doing manifest rewrites. All those maintenance operations that Iceberg offers, the Tabular platform intelligently will handle for you, and you can just get optimized tables for your queries downstream. All right, so with that, I'm going to go ahead and jump over to the Tabular UI. Are we seeing this? Good. Okay. So this is the Tabular web application. Everything I'm going to show here is also available through APIs or using compute engines, but this is just a convenient way for us to see what's going on. So I've got here in my Tabular organization, I happen to have two different warehouses, one that's backed by AWS S3 bucket, another one that is backed by GCS. I'm going to go ahead and dig into this enterprise data warehouse where I have a couple of examples spun up. And the first one we'll go is in this batch raw database, and we'll show an example of what this file loader would look like doing batch loads from S3. So I have the serverless weather data. Here's a schema. This is actually JSON data that's being dumped from a weather service, weather application on some regular frequency. And so it's got a pretty complex schema. The JSON files have nested structures, and it's quite complex, but the system handles all this and schema evolution elegantly. And we can also see right away some of the value of the automated maintenance activities that Tabular is performing on this data. So here in the top right, we can see, over the last week in this table, we've taken, over 18,000 files, raw files that have been coming in, and it's currently, 663 actual data files. So that will result in much better performance for all of our queries downstream, Spark or Trino or Athena, what have you. In addition to getting those files compacted, the Tabular platform also does a lot of optimization in terms of how to cluster that data, what are the right compression codecs to use, things of that nature, and actually reduce the physical size on disk. So instead of having, this is small data because it's a demo, 200 megabytes, we only have 30 megabytes of Parquet. And so you're saving on S3 cost. And again, your compute queries will be just much more efficient because there's less IO they have to do to read data from disk. And this is true, obviously, with JSON, but happens with Parquet and other file formats as well. What does that look like from actually how does this stuff get configured in Tabular? We saw on the slides, setting all those settings for a file loader. So here in the UI, we're going to show a bunch of that stuff. There's also a bunch of configuration here for doing all those maintenance activities. So again, managing historical snapshots. As Vicky alluded to, you may not want to keep, all of history. In this case, we're actually keeping, a whole year's worth of history in this table, but we could set this to whatever value we wanted to. And Tabular will automatically go through, expire the snapshots, as well as run the orphan file cleanups to remove those objects from the object store, so you're not, wasting S3 space. Automatically doing compaction, we saw the value of having compaction enabled on these tables, especially that are loading small files. And here's where the file loader is actually, being configured. So we're just pointing to this path on S3. We're telling Tabular that this is JSON file coming in, and we can choose other formats, and then we want it to be appended to the table. And so there's constantly going to be appending data to this table, as well as cleaning up all the old snapshots and doing compaction. So we get a very optimized Iceberg table, from raw JSON files, just through configuration. So no code necessary and no infrastructure. And just to take a peek at the activity logs, So obviously, you can look to see all this activity that Tabular is doing on this table's behalf. And you can see there's rewrite manifest operations that are happening. This is the metadata compaction. Here's file loading actually happening. We're loading up these JSON files. And there's going to be compaction activity here as well that shows compacting all the small files together. So you can take a look to see what's going on in the table. So that's an example of this batch loading. Make it really, really easy to batch load data into Iceberg tables without having to run. You don't have to run any crons or schedulers or worry about running any infrastructure to do that. The next example I want to show is a Kafka Connect example. So I'm not actually going to show the Kafka Connect infrastructure. You have to run some Kafka Connect nodes in order to be able to produce this data, but we'll just see the result of that in Tabular in the Iceberg table. So here's an example, going back to what Vicky showed, where we've got Debezium reading from a Postgres bin log, and we're going to write that change log through Kafka and then write it to an Iceberg table. This is going to be a record of everything, all the changes that happen in the database. So all the raw history, kind of in an append-only fashion. So we get a persistent change log in an Iceberg table. And then we'll also show how we take that change log and turn it back into a mirror of the transactional system and actually apply all those changes through merge operations and get back to a state that looks like our transactional system. But here we've got a Kafka Connect system that's writing, and you see here, this is writing 3 times per minute. So we've got this every 20 seconds, we're committing that change log to our Iceberg table. So there's gonna be lots of updates going on here. But again, the Tabular system is gonna go ahead and make sure that table gets optimized over time. So we can come in here, this has got a relatively simple schema. We can see all of our change data capture metadata here, what the operation is. Was it an insert, an update, a create, what the offset of that bin log was, timestamps of when that event happened, as well as the sort of the key that would represent multiple changes to a particular database record over time. And we're going to have that entire change log, and we're going to use that information when we go to merge these changes into a downstream table. So similarly, incredible work by the file compactor here. Instead of having 3,500 files, you've got 4, and we're also getting some savings on the S3 storage side. That's nice to see. And from an activity perspective, we can see, here's table compaction where it's, taking 400 data files and turning it into one, right, over time, as well as if we look at the snapshot history of a table, we're going to see every 20 seconds. So lots and lots of snapshots. This table has 3,600 snapshots, but over time, Tabular will make sure that those get cleaned up and any files that are associated with those snapshots cleaned up over time. All right. So that's the Kafka Connect changelog. And then the last thing I want to show is how we actually get back to a transactional, a mirror of our transactional database. So this isn't so much on the ingestion side, but it's worth calling out here since we were talking about this use case. Tabular has another feature which allows you to take a raw changelog, like a Debezium changelog, and we'll automatically do incremental processing of that changelog and merge the changes back into an Iceberg table that is ultimately a mirror of your transactional table. And the way that we do that is to set up a couple of table properties. So here, this is the raw changelog, and we're saying, hey, there's a downstream table that it represents the mirror, the transactional mirror of this changelog. And so I'm going to pop over to that table, and we can see some of the settings over here. So this is going to be the table that is the reflection of our transactional table. So we've merged all the raw changes into, we only have a single record per key that has the latest value, and we're also doing the deletes as well. So we're really getting a true mirror of the transactional system here. And this is just driven by, again, a number of table properties. If I scroll down, where we're saying, hey, this is a CDC type of merge. This column represents the ordering column, so we know we're processing the events in the right order, and this column represents the key that we're going to merge on. So again, just your configuration, no scheduler necessary, no code or infrastructure necessary. You can get all the way from a transactional system into a mirror in an Iceberg table. All, this is on order of minutes kind of latencies. So some of the features in Tabular that really take the power of Iceberg, the specification and the table format, and use all the features of Iceberg to really solve some challenging like ingestion problems at scale. So I'm going to pause there and dig into the Q&A. So if you have questions again, please do drop them in the Q&A. We've got another sort of 15 minutes here to answer questions. The first one here is in Azure, what options are available for catalog store, e.g. glue in AWS? Unless I'm mistaken, I don't think that Azure has a native option for an Iceberg catalog the way that Amazon has glue. So I think your best option would actually be Tabular. And if you're in Azure, so we've got early previews of Azure support in Tabular. We're going to be building that out in the coming months. But if it's something that you're interested in trying in Azure, please do reach out to us, and we'd be happy to get you access to some of our Azure support. But I don't think there's a glue equivalent in Azure. You'd have to run either your own catalog, which you can certainly do. You could run your own REST catalog or JDBC catalog, or even Hive-based catalog for Iceberg, or use something like Tabular. The next question, are you currently using Flink upsert in your production use case? The challenge I found is the equality delete file makes read super slow.
I can take this
Vicky, do you
one.
want to take this? Yeah.
Yeah, so we are not, like at Tabular, we're not using Flink, but in general, because I've seen this issue with equality deletes in Kafka Connect, is like, yes, the quality delete will always be less efficient than the positional delete. And that's because with the positional delete, you're specifying the exact file, the exact position in that file that you want the filter to happen. Where with the quality delete, you have to almost look at every single file. So how do you get around this? So I think it depends a little bit on your use case. But for example, when it comes to the changelog data, like throughout the presentation, we've been talking about what it takes to mirror a production table in Apache Iceberg. So you have a couple options. So one is to have one changelog table. So it's just ever appends. And then what you do is you have a separate table where you're actually performing the upserts at a different cadence, right? And in that scenario, you're only doing copy on write. You can even go one step further and say, I'm going to have that plus a view to attach the I guess the tail end, like the bleeding edge of my changelog table to that table. So you could express that as a view. That's one option. I find that you can't rely solely on equality delete files. You should be using a combination and writing positional deletes when possible. But if you're at a scale where your equality delete files are that's the bottleneck of your operations, you need to switch to a completely different pattern. And unfortunately, that's just like the nature of having to go really far back. So that's why having separate tables, having some sort of view in between can actually be like a really good pattern to use.
Yeah, you can sort of see this in what I demonstrated. Like for Tabular, our recommended approach is the two-table approach that Vicky illustrated, where we actually just from the stream, we want the stream to be append only to really like make sure that we have low latency throughput from the stream, and the stream doesn't back up. And then from there, once we have that history, it's also nice that we have a history of the entire changelog in an Iceberg table. That's very valuable for going back in time, troubleshooting, restating data. But from there, we'll take that and merge that into a downstream Iceberg table. And still, whether we use copy and write in doing that merge or merge on read, there's trade-offs there. And if you are going to use merge on read, even in that secondary layer of a table, you have to aggressively compact the equality deletes because, as Vicky mentioned, equality deletes basically every single reader who reads the data file also has to read every single equality delete to apply that filter on top. And so you're paying a pretty big tax. And it can be okay if you just you really want to maximize your write throughput, but you have to aggressively compact those equality deletes. And Tabular, that's something the Tabular platform does help with, is being smart about compacting those equality deletes away. Okay. Next question is, can you provide insight into the current state of analytics engines supporting the REST catalog and tabular strategy regarding it? Some integrations with analytics engines appear overly complicated due to external engines not supporting the REST catalog. Okay, do you want to take that, or I can handle it? Yeah, okay, I'll take this one. All right, so current state on REST catalog. All the open source engines have very robust support for the REST catalog at this point. So Spark, Trino, Flink, Kafka Connect, those are very robust in their support for REST catalog. Beyond that, I think there's ongoing work in the commercial engines for REST catalog. So those are things like Athena, Snowflake, BigQuery, Dremio. There are probably others that I'm forgetting. For support for REST catalog. So, those are obviously on the cadence of the owners of those systems. And, there is work happening in all those systems. And we are talking. So what's Tabular's strategy? Our strategy is to help those engines and those vendors get robust for REST catalog, because we know that's the direction that the Iceberg community is really going in, and where a lot of the new features are landing. And B, obviously, Tabular's catalog is a REST-based catalog. So we want those engines to be able to interact with everybody who's using Tabular for their catalog and storage management. So we're very vested, obviously, in getting that work done and making sure that it's done well. All right. Next question is there a rule of thumb to follow when using copy on write versus merge on read in CDC ingestion use cases? For example, if merge on read generates X amount of delete files, then it's better to use copy on write. Vicky, sort of talk about the trade-offs there again.
I can try. So I don't have an exact number to give you about, like, if you hit this threshold, you should switch from one pattern to another. I don't have like that kind of heuristic for you, but what I can say is we now understand the tax that you have to pay for using the equality delete file. So if you have a situation that can actually use the positional deletes, that's a good situation for merge on read. So for example, if you have a CDC log and your CDC log is going to have lots of create statements. So this is, you don't have to look in the past for the row. And if it is going to get updates, it's most likely to occur within the same file. Like maybe you get updates really close to each other. That's just the nature of performing a transaction. And then afterwards, the row kind of stays stagnant. That's a really good opportunity to rely on merge on read, because you're mostly going to be using positional deletes, which are cost effective. So I think you have to look at your use case and what the data coming in actually looks like.
I think the call out there is just to make sure your downstream engines that you're using will support reading the Iceberg V2 stuff and support reading all the delete files. Because again, not all the engines currently support that, and most are. If they don't, everybody is working on it. But just something to double check on before you go down the merge on read path is check your downstream engine support. Yeah, the other thing I would say there, and this is just a general recommendation for any of these update use cases like CDC, and what our system does when it's doing CDC processing is really think strongly about how you're clustering data. You want to cluster the data in a way that you can quickly identify records that likely need to be updated. So if you know that your update pattern is like, we only update data that's happened in the last day or week or month, you can use that to your advantage and partition and cluster in a way that makes the writes and the reads more performant. And yeah, the view combining a sort of compacted CDC merge table with the change log for just the most recent changes, and having a view there, so you sort of get the best of both worlds. You've got the most up-to-date data that's in that change log, but also relatively performant because you are compacting that change log into another table over time. That's a really nice trade-off for latency and performance. Next question. Does the Iceberg Kafka connector support using a regular expression for the list of Kafka topics, or does each topic need to be explicitly specified?
I believe you can give it a regular expression.
Yeah, I'm 95% sure that's true. Yeah. You can do I think you do regular expression. Oh, we got confirmation from thank you from the audience. So that's awesome. Um, and if I think there's maybe a follow up about tables and routing. I think all of that can be done dynamically through regular expressions. I think most of those configuration properties in the Kafka Connect support sort of regex and dynamic mapping. Um, General question. Once tables are ingested, loaded into Iceberg, especially with respect to tabular, automatically discovering and creating new tables or schema evolution, how would clients like Trino or Spark discover, realize the existence of those newly arrived data lake changes? Does the Iceberg catalog, e.g. the REST catalog, automatically allow Trino to see the tables? Yes, I think the answer to that is yes. The catalog is the thing that all the engines go through the catalog to figure out what tables exist, as well as what is the latest state of all those tables. And so, yeah, it is auto magic. It's not a magic, obviously, in that case, but yeah, the catalog is really key for producers and consumers. That's that interaction point to make sure that everybody's talking about the same version of the table. Next question is, what various impacts, locking delays, etc., do readers incur during table compaction events?
I can talk about that. So this is where optimistic locking is our savior, because compaction can take a long time and you don't want to be holding the lock, let's say for like 30 minutes of like your catalog for that table, not allowing for new updates to come through. So what's happening when you have like a compaction on process happening is actually that compaction's happening in the background, but the lock is free. So we can have other writers starting to append. And only once all the writing of the compaction process is finished and it's now ready to commit to the table, its changes, will it then grab the lock, check to see if its changes are actually compatible, make any metadata changes it needs to make, and do the commit. So there is actually no delay. All those, because of the optimistic locking, all those incremental writers that are, say, just doing append operations, they can keep going.
Yep. Yeah. So compaction is going to interfere with readers or writers at all. The only thing to be aware of is if you are doing updates, you can run into real conflicts, right? If a compaction job is trying to take file A, file B, and turn it into file C, and during that same time, an update is trying to update file A. Well, now you've got two writers that are actually trying to modify the same exact file. That will run into real conflicts, and you'll basically have to redo the compaction or the update, sort of whichever comes first. So the first one is going to win given the optimistic locking scenario. The tabular catalog, also the tabular backend, has some intelligence built in here where we can prefer the updates and basically make sure that the compactions are the things that don't interfere with write. So you can do some very sophisticated things with the REST catalog if you understand the Iceberg spec. All right, next question. I've set up the Iceberg Kafka sync for Mighty SQL CDC changes into our Iceberg table. Awesome. One challenge I have faced, prototyping the merge pattern, is the bin log timestamp is second precision. There are multiple updates to the same primary key in the same second. Are there patterns to overcome this issue? Vicky, you got this one?
Yes, there are solutions to this issue. I feel like, and if people want this, I could do a whole presentation just on CDC and Debezium and what these events represent, because there's so many different timestamps and they all mean and communicate different things. But when it comes to picking the right row, the most important thing is the ordering. And when the events get submitted by a tool like Debezium to Kafka, you don't actually have to look at the timestamp anymore. You can rely on the ordering in Kafka, how the event made it to Kafka and in what order. So what you can do is actually rely on the Kafka partition and offset to give you the right order of which version should I pick. So that partition offset should trump whatever timestamp value is in the event.
Yeah, awesome. And do you support cross-cloud replication, e.g. AWS to GCP? Vicky, this is your wheelhouse again.
It's coming in Tabular. We are working on it. This is one of the key features that Jason and I are working on right now.
Yeah, likely being a delivery here in the next month or so. It's got some stuff running in dev. We are currently evaluating the glue compaction support in AWS. How does that compare to your solution? I'll take this one. I haven't spent a ton of time looking at the AWS glue compaction. It's a relatively new feature for them, but the little bit I've looked at it, it is I have two big differences. The first one is in order for it to work, it's based on turning on CloudWatch events for your buckets. That's fine, but it can be very expensive to get college events happening on everything happening in S3. So there's a cost factor there to potentially look out for. The other one is it's relatively naive compaction, right? It's not thinking about the write and read patterns to your table. Tabular, when it decides to do compaction, is quite sophisticated. It will look for your write patterns, historical write patterns, and it's like, hey, if I see 10 1 MB files come into this table, maybe I should compact, but maybe I should wait because maybe there's 10 more 1 MB files coming to this table in the next 5 minutes, and I don't want to have to recompact data multiple times. So just given our experience running compaction and Iceberg tables for many years, I think ours is just much more sophisticated. And also, it looks to be less expensive generally. Like the way that we charge for compaction is based on total bytes sort of processed. In Glue, you're paying for Glue Spark instances or whatever they're running behind the covers. It's ultimately be more expensive depending on your use case. All right, next question is any insights on how best to use Beam on top of Iceberg?
I mean, I'm not a big Beam user, like I just don't have that much experience with it, but my understanding is it's quite similar to Flink. Now, what might be missing from Beam is the Iceberg IO implementation, which I know is something that Google is working on because data flow in Google it runs Beam. So they want data flow to be capable of reading and writing from Iceberg tables. So that's something to check out and investigate. But one thing about like Beam or Flink that's actually quite cool that people don't often talk about is like Flink, for example, can read and write from Iceberg tables. So it's sort of interesting to think about Iceberg as like an alternative from like a stream like Kafka, where you can actually tail the changes that are happening to the table. So just something to like think about. There's actually some cool patterns that you can leverage if you're going to use something like Beam or Flink for analytics for near real time, not real time, but near real time analytics.
Yeah, there's definitely work happening recently in the Beam community with Iceberg support. I know we've got Tabular customers who are interested in that, and we've got even folks inside Tabular who are working on Beam support along with the Google folks. Since the Tabular Iceberg catalog auto-magically updates, I love it, and auto-evolve schemas, is it safe to say you could use an upstream registry, i.e. the Confluent schema registry, as a source of truth and feel okay about Iceberg's ability to stay in sync with the upstream changes? Yeah, I think that's a safe thing to do, and we have customers who are doing exactly that. That's a very reasonable pattern with schema registry and Tabular. On what frequency is the automatic compaction being run by Tabular? Also, as a follow-up, can Tabular users force the compaction or change the frequency? So I talked about a little bit that the frequency is actually not fixed. It's intelligent, and it really varies by table based on the write patterns. And so given that, there actually isn't a way to there's actually a way to force it to run, but there isn't a way to change the frequency. It's not a fixed interval, so it is dynamic. The good news is that we've got lots of customers, obviously, who are taking advantage of this feature in Tabular, and I don't know of any who have ever changed it from just using the default settings because they're quite ideal for they're good for a variety of use cases because they are adaptive to the table. Does Tabular offer on-prem/Helm chart deployment, or is this a completely managed solution? FYI, we're on Azure. All right. Well, we talked about Azure support coming, so please reach out to us after this if you want to get some preview access to that. But beyond that, it is a completely managed solution today. There's no on-prem or Helm chart deployment. It's a service. And last one here, because we're over time, our Iceberg table is exposed via tabular read-only from the perspective of external analytics engines. It depends is the answer. For engines that have full REST catalog support, so we talked this a little bit, your Sparks, your Trinos, your Flinks, and there are a few others who have full REST catalog support, then that's read and write. If they're using the REST catalog, they're using just all the Iceberg open source stuff to both read and write to tables. In other situations where they don't have REST catalog support, Tabular basically is syncing our catalog to those places, so things like Snowflake and BigQuery, and those are read-only because they're not actually coming through the REST catalog. Awesome, Greg. I'm glad it was informative for you. Thank you for the positive feedback. We will take all feedback either now, or you can find us in the Iceberg OSS Slack. There's a vendor Tabular channel there. We're always hanging out in there. You can ask questions, or feel free to reach out any other way you can find us.